captions in English, please. So this is the second video of chapter 9, and we will go over how to do mass-to-mass conversions. Mass of a reactant or product of a chemical reaction to mass of another reactant or another product of a chemical reaction. So it's mass-to-mass conversions with the fact that you need to go through moles. Because a chemical reaction contains conversion factors between moles of reactant and moles of product. So it's all in relationships of moles. But we are often interested in relationships between mass of reactant and mass of product, because when you're in a laboratory, you can get the mass, but you don't count moles. So the general outline for this type of calculation is like this. First, you will need to change the mass of your substance A that is known. You know, you got it from a balance. And you can change it to the moles of A because you know the molar mass of A. So for this conversion, you need to know the molar mass of A, the substance A, to change its mass to its number of moles. The second step is to change the number of moles of A to numbers of B. And for this, you need the chemical equation and the mole ratio between moles of A and moles of B. And once you have your moles of B, you can go back to grams of B using the molar mass of B. So for this, you need to know the formula of the substance B. And that's how you can get the mass of B, knowing the mass of A that reacted. So that's the general form of those mass-to-mass conversions. Let's go through an example with the reaction of iron 3 oxide with carbon monoxide. So you're given the chemical equation. It's iron 3 oxide solid plus 3CO, that's carbon monoxide, will produce 2 iron solid plus 3 molecules of carbon dioxide gas. So the question is, how many moles of iron will be produced from 152.6 grams of carbon monoxide if you have an excess of iron 3 oxide? So we want to know the number of moles of iron from a mass of carbon monoxide. So we start with the mass of carbon monoxide. It's one of the reactant, and we want to know the number of moles of one of the product. The balanced chemical equation gives us a relationship between moles of carbon monoxide and moles of iron. But that's between moles, and it says 3 moles of CO equals 2 moles of Fe. We use the coefficient from the chemical equation to get that mole to mole ratio. And so from this, we can get two conversion factors, 3 moles of carbon monoxide over 2 moles of iron, or vice versa, 2 moles of iron over 3 moles of carbon monoxide. But before we can use that relationship, we need to convert the grams of carbon monoxide into moles because the given amount is in grams of carbon monoxide. So we will need to change 152.6 grams of carbon monoxide to moles of carbon monoxide. So that means the concept map will look like this. First, we have the grams of carbon monoxide, and we will change them to moles of carbon monoxide. And then we can use the coefficient from the chemical equation to change the moles of carbon monoxide to moles of iron. So to change the grams of carbon monoxide to moles of carbon monoxide, we will need the molar mass of carbon monoxide. And then we will use the mole ratio from the chemical equation to do the change from moles of CO to moles of Fe. So the molar mass of CO, carbon monoxide, is 1 time the molar mass of carbon, 12.01, plus 1 times the molar mass of oxygen, 16.00. You add them together and it's 28.01 grams per mole of CO. Next, we need the mole ratio between carbon monoxide and iron, and we see from the chemical equation above that we need 3 moles of carbon monoxide to make 2 moles of iron. So the next step is to write the solution. So the given amount was 152.6 grams of carbon monoxide. So that's the given amount. It's written first, and it's in the numerator. You could have a line under and a 1 in the denominator. So that's in the numerator. You multiply by the first conversion factor that changes the grams of carbon monoxide to moles of carbon monoxide. So the molar mass of carbon monoxide is such that the grams are on the bottom, the mole on top, so that we can cancel the grams of carbon monoxide. The second conversion factor needs to cancel the moles of CO. So we have moles of CO on the bottom and the moles of iron on top. So um, this way we cancel the moles of CO units. So here, what came up here, the mass, so the first part of the calculation, the 152.6 grams of CO times the 1 mole of CO over 28.01 grams of CO is allowing you to change the mass of the substance A, carbon monoxide, into the moles of substance A, which is carbon monoxide. So that's the first conversion. And then the second calculation that uses the intermediate answer from the first calculation times the second conversion factor here is about doing the mole to mole conversion. So from moles of carbon monoxide, we will change that to moles of iron, because we see that the moles of carbon monoxide cancels and we are left with moles of iron. So the calculator answer is 152.6 times 2 divided by 28.01 and divided again by 3. Or you do 152.6 times 2 divided, open the parentheses, 28.01 times 3, close the parentheses, equal. And it should be the same answer. And it's a 3.632036, etc. Here, the given amount had this 4 sig figs. So you keep 4 sig figs because all the 1 mole, 2 moles, 3 moles are exact numbers. And the molar mass is also 4 sig figs. So you keep 4 sig figs in the end. And so that's the mole of iron that you can produce from this mass of carbon monoxide. Let's go through another example, and we will use the combustion of octane. So you're given the chemical equation that shows how octane burns with oxygen to form carbon dioxide and water. And we have carbon dioxide and water as product because it's a combustion reaction here that burns a compound made of carbon and hydrogen. So what mass of carbon dioxide is emitted by an automobile per 5.010 to the 2 grams of pure octane used? So octane, as a reminder, is part of the gasoline. But here we imagine that the gasoline is pure octane. So that means we have this formula, C8H18 is the pure octane. And we have a mass of it, so 5.010 to the second. And we want to know how many grams of carbon dioxide, is emitted. So from the mass of octane that is given, we want to find the mass of carbon dioxide. So the balanced chemical equation gives us a relationship between the moles of octane and the moles of carbon dioxide, not between the masses. So to go from mass of octane to mass of carbon dioxide, we will need to go through moles because we can only change the moles of octane to moles of carbon dioxide. We cannot change the grams. So we will need this mole ratio that says that, from the chemical equation, we see that 2 moles of octane will produce 16 moles of carbon dioxide. And so that will lead to 2 different conversion factors. But first, let's write the concept map. And it shows that we will need first to convert those grams of octane into moles of octane before we can use the mole ratio between octane and carbon dioxide. And then once we have our moles of carbon dioxide, we can go back to grams of carbon dioxide because the question is asking for grams of carbon dioxide. So for the first step, from grams of octane to moles of octane, we will need the molar mass of octane. Then when we will convert moles of octane to moles of carbon dioxide, we will need the mole ratio that we will obtain from the chemical equation. And it's the 2 moles of octane equals 16 moles of carbon dioxide. And then to change the moles of CO2 into grams of CO2, we will use the molar mass of CO2. So let's find out those values. So molar mass of C8H18. So you take 8 times the molar mass of carbon, 12.01, plus 18 times the molar mass of hydrogen, 1.01. You add all of this together and it's 114.30 grams per mole. So that's the molar mass of octane. We also need the molar mass of CO2, and that's 1 time the molar mass of carbon, 12.01, plus 2 times the molar mass of oxygen, 16.00. And you add this together and it's 44.01 grams per mole of CO2. The last equality we will need is the mole ratio that says you produce 16 moles of CO2 from 2 moles of octane. And that's obtained from the chemical equation, the balanced chemical equation. So we are ready to write the full solution, and for this we will start the calculation with the grams of octane that was given, and that's 5.010 to the second grams of octane times the molar mass of octane such that the grams are on the bottom and the mole on top, so that we can cancel the grams of octane. This first calculation allows you to change the mass of substance A into moles of substance A, and A here is the octane. The second conversion factor needs to cancel the units of moles of octane, and that's the mole ratio conversion factor here, with the 16 moles of CO2 on top and the 2 moles of octane on the bottom, so that we can cancel the units of moles of octane. And so when you do this calculation, it comes down to convert the moles of substance A, which was octane, into moles of substance B, and that's carbon dioxide. Next, you need to change the moles of carbon dioxide into grams of carbon dioxide. So you will multiply by the molar mass of carbon dioxide with the grams on top and the mole on the bottom, so that we can cancel the moles of CO2. And that leaves us with grams of CO2, which is what the question was asking for a mass of carbon dioxide produced. And this last step allows you to change the moles of B, which is carbon dioxide, into mass of B, which is mass of carbon dioxide. And so in the calculator, you do 5.0 second EE2, so times 10 to the second, times 16 times 44.01. So I multiply all numerators together and then I divide by each denominator. So divided by 114.30 and divided again by 2. And that's 1540.15748, etc. So that's grams of CO2. So that's the calculator answer. Here we have 2 sig figs in the given amount. The moles, all the mole numbers are exact numbers. So you know the 2 moles of octane, 16 moles of CO2, and the 1 moles for the molar mass are all exact numbers. Both molar mass have more sig figs than the given amount. You know, molar mass of CO2 has 4 and the molar mass of octane has 5. So the limiting amount is 2 sig figs from the given amount. And so 1,500 would be the answer here. And here it's given in scientific notation. So it's 1.5 10 to the third grams of CO2. So that's 2 sig figs. And so 500 grams of octane will release uh, 1,500 grams of carbon dioxide. So it's uh, it's a lot of carbon dioxide released. So let's do a concept check. So let's read this. The first step in producing calcium dihydrogen phosphate, a water-soluble fertilizer known as triple superphosphate, is to react calcium phosphate with sulfuric acid to produce phosphoric acid and calcium sulfate. So this is the reaction in words. And the question is how many grams of phosphoric acid would be produced if 6.75 grams of calcium phosphate were present at the start of the reaction. So first you want to write the equation, and maybe the by words is a first good step here. It says the first step in producing calcium dihydrogen phosphate, a water-soluble fertilizer known as triple superphosphate, is to react. So this is not even part of the equation. It's just the first step of a series of reactions that will lead to ultimately to calcium dihydrogen phosphate. Where it starts is here, is to react. So we are reacting calcium phosphate with sulfuric acid, calcium phosphate with sulfuric acid to produce phosphoric acid with calcium sulfate. So that's how it is in words. That's the equation or chemical reaction we are interested in. So let's change that into formulas. So we have calcium phosphate. Calcium is the Ca2 plus ion because calcium is in group 2A, so it's always a 2 plus ion. Phosphate is a polyatomic ion, and so you can look at your list of polyatomic ion, and that's the PO4 negative 3 ion. So together, if you do the crisscross trick, you can see that we will need 3 calcium for 2 phosphate. So it's going to be calcium 3 and PO4 2. So we need 2 phosphate for 3 calciums, so that 3 calciums times 2 pluses will be 6 positive charges in total, and then the 2 phosphate with each 3 negative charges, that's going to be 3 times 2, 6 negative charges in total. So that's the formula, and if you look at your solubility rules, you will find that it's a solid, because phosphate leads to insoluble compound, and calcium is not an exception. Now let's find the formula of sulfuric acid. So sulfuric here, there is no hydro in front, so we know it's an oxyacid, and the ending "ic" suggests that it comes from the polyatomic ion ending in 8. So you take sulfuric and change the ending to 8, and that means the sulfate. And the sulfate is SO4 negative 2. Look at your list of polyatomic ion for that. That's an acid, so it combines, the sulfate combines with the H plus ion to make an acid. So we have H plus and then SO4 2 minus. If you do the crisscross trick here, you see that you need 2 H for 1 sulfate. This way you will have 2 positive charges cancelling the 2 negative charges on the sulfate. Acids are always aqueous, so this is aqueous. Now, phosphoric acid. No hydro prefix means it's an oxyacid. The ending "ic" means it's the phosphate ion. It ends in 8. Phosphate is PO4 negative 3. Look at your list of polyatomic ion for that. And that's an acid. That means the positive ion is the H plus ion, the hydrogen plus ion. If you do the crisscross trick, you see that you will have 3 H for 1 phosphate, because you need 3 positive charges to cancel the 3 negative charges on the 1 phosphate. So the formula of phosphoric acid is H3PO4 aqueous. Aqueous because acids are always aqueous. And finally, calcium sulfate. Calcium again is Ca2 plus because it's from group 2A, it's a predictable ion. Sulfate, we've seen it's CSO4 negative 2. Here you see two positive charges and two negative charges. So the formula of the compound is just one of each ion, and it's CaSO4. If you look at your solubility rules, you will find that the sulfate makes mostly a soluble compound, except when it's with calcium, barium. So calcium sulfate is actually solid, even though sulfate typically makes soluble compound. So that's our skeletal equation here. It's not balanced. So the next step is to balance it. Let's count the number of atoms of each type from both sides of the equation. And so we have 3 calcium on the left and 1 calcium on the right. 2 phosphate on the left, 1 phosphate on the right. 2 hydrogens on the left in the sulfuric acid, and then 3 hydrogens on the right in the phosphoric acid. 1 sulfate and 1 sulfate on the right. So we see, so when you have polyatomic ions like that, like the phosphate and the sulfate, you want to balance the polyatomic ions first. And here phosphates are not balanced, so let's make it 2 phosphate on the right by having a coefficient of 2 on the right. And so that coefficient of 2 should be in front of the molecule that has the phosphate, and that's phosphoric acid. So place a 2 there. We need to balance the calciums. There are 3 calciums on the left, only 1 on the right. So let's have a coefficient of 3 for the calcium sulfate, so that we'll have 3 calciums on the right. So that balances the calcium and the phosphate. However, when you place those coefficients of 2 and 3, it changes the number of hydrogen and of sulfate on the right. So let's recount the number of hydrogens on the right. We have 2 times 3, 6 hydrogens on the right. And because of the coefficient of 3, we have 3 sulfate on the right now. So 6 hydrogens on the right, only 2 on the left. So to make it the same, let's make it 6 and have a coefficient of 3 in front of the hydrogen, on the hydrogen side. And the sulfate, to have 3 sulfate on the left, we also need a coefficient of 3 in front of H2SO4. So by having this coefficient of 3, it balances the hydrogen because it's 3 times 2, 6 hydrogens now on the left. And now we also have 3 sulfate on the left. So that balances this equation. So that was just establishing the chemical equation. But the question is how many grams of phosphoric acid would be produced if 6.7 grams of calcium phosphate were present at the start of the reaction. So let's rewrite everything there. So we have our balanced chemical equation and the question. The question is asking for grams of phosphoric acid, knowing 6.75 grams of calcium phosphate are present at the start of the reaction. So the first step will have to be to change the grams of calcium phosphate, into moles of calcium phosphate, because we cannot change the grams of a substance to grams of another substance without going through moles. The chemical equation gives us proportions in moles, but it's not in grams. So you have to change the grams of phosphate into moles of phosphate first. Then, using the chemical equation coefficients, you can change the moles of calcium phosphate into moles of phosphoric acid. And then go back to grams of phosphoric acid once you have the moles of phosphoric acid. So that's the roadmap for this calculation. So the first conversion will require that we have the molar mass of calcium phosphate, so the molar mass of Ca3PO4 2 times. And the second step will require that we do a mole-to-mole conversion. And for this, we will use the chemical equation coefficients that are given here above. And then finally, to change the moles of phosphoric acid to grams of phosphoric acid, we will use the molar mass of phosphoric acid, which is H3PO4. So let's calculate those molar masses. Molar mass of Ca3PO4 two times is 3 times the molar mass of calcium, which is 40.08, plus 2 times for the 2 phosphorus, we need 2 times the molar mass of phosphorus, which is 30.97. And then be careful, you have 8 oxygen. You do 4 times 2, 8 oxygen, because you have 2 phosphate, and each phosphate has 4 oxygen. So it's 2 times 4, 8 oxygen, so times 16.00, the molar mass of oxygen. You add up all of this, and it's 310.18 grams per mole of calcium phosphate. We also need the molar mass of phosphoric acid. Phosphoric acid is H3PO4, so you take 3 times the molar mass of hydrogen, so 3 times 1.01, plus 1 time the molar mass of phosphorus, 30.97, plus 4 times the molar mass of oxygen, 16.00. You add all of this together and it's 98.00 grams per mole. And finally, we need the mole ratio, which is obtained from the coefficient of the chemical equation. And here it's between phosphoric acid and calcium phosphate. And we see that we have 1 mole of calcium phosphate reacting and producing 2 moles of phosphoric acid. So 1 mole of calcium phosphate will give 2 moles of phosphoric acid. So now we are ready to do the calculation, and we'll start with the given amount of 6.75 grams of calcium phosphate that we will multiply by the first conversion factor that comes from the molar mass of calcium phosphate, such that the grams are on the bottom, so we can cancel the grams of calcium phosphate. So the mole of calcium phosphate is on top. So this changes the grams of calcium phosphate into moles of calcium phosphate. The second conversion factor needs to change the moles of calcium phosphate into moles of phosphoric acid. So for this, we use the mole ratio. And so we want the mole of calcium phosphate on the bottom so that it cancels the unit of moles of calcium phosphate. And we have 2 moles of phosphoric acid on top. So this changes the moles of calcium phosphate into moles of phosphoric acid. The next step is to change the moles of phosphoric acid to grams of phosphoric acid using the molar mass of phosphoric acid. And so we will use the molar mass such that the grams are on top and the mole on the bottom, because this way we can cancel the units of moles of phosphoric acid. So in the calculator you do 6.75, and I will multiply all numerators together, so times 2 and times 98.00. And then I will divide by the denominator 310.18. And the calculator answer is 4.265265, etc. Here the given amount is given with 3 sig figs. The molar masses have 4 and 5 sig figs, and the number of moles are all exact. So the limiting number of sig figs is from the given amount, and it's 3 sig figs. So we need to keep the 4.2. 6, what comes after the 6 is a 5, so you round up into a 7. And so it's 4.27 grams of phosphoric acid. And if you look, does it make sense? So basically the molar mass of phosphoric acid is 100 times 2 on the numerator. So it's 200 over something very close to 300. So basically it's 2/3 of the given amount, and 4.27 is about 2/3 of 6.75. So that makes sense.